Thanks for the invitation. Yeah, I'm now a lecturer at Mary, and I'm going to talk about the challenge of missing modalities and scarce data in the multimodal learning. Okay. The focus of my research is about these three R's, or this R-cube, because we want to make the machine learning or AI in the system to be reliable, responsible, and also can be well regulated, say. And here we mainly we're concerned the reliability issue of multimodal learning. So here I'm not going to talk about this generative models because I mean in the real world we care more about the decision-making models. So yeah, let's go back into those classical domain of multimodal learning. So we just have those features, and the model will output some decision based on this input data. So here we consider like two applications. Let's say the first one is how to based on how to make the prediction based on this multimodal input in the medical diagnosis data. Like here we consider the X-ray image and also the EHR data, the electronic healthcare record data, and also we consider how to make the recommendation based on the language and image on the internet. Okay, so the reason why we care about the missing modality is that it's possible that you have some financial constraint, or you have some time constraint that you can't have the full modality data. Like in the medical domain, you might have limited time, like in the survival prediction. You need to predict whether the patient will live or die after maybe 8 hours, let's say. So you don't have that time to collect a lot of data, so you have this missing modality issue. And in some general domain, maybe this large-scale data set is multimodal data. It's called the Lion 5 billion. But in this data, it's not like the traditional data ImageNet. The ImageNet is like a centralized data, right? They have a server, and you have the access to the data, and you just download the data from their server, right? But here, Lion data is like they give you some URLs, and you just go to their website and you download this data. So it's possible that you don't have well-paired image and language at the same time, because the URLs may not be available at the time of you download this data, right? Okay, so here we consider the scenario that we have a pre-trained multimodal learning transformer, let's say, and then we are going to fine-tune this model in this very low data domain. Like during the pre-training, you have very large data set, but in the real world, in a hospital, you don't have that much data during the fine-tuning stage. So maybe you only have several hundred samples, or maybe 10 samples, maybe. So I guess the popular way to address this is, you can imagine, okay, we have very strong generative models, we just generate this data. But if you want to train a well-performed model, a well-performed generative models, you require a lot of data, right? Because those generator needs a large amount of data to perform quite well. I mean, so if you have very limited data, then that's not something you want, right? And also, I'm concerned about the reconstruction computation because, you know, if we generate some data, okay, that's the raw data. For instance, in the image, it's in the pixel space. But during the training, you're going to, you know, encode the pixel data into a feature space. So this process is kind of a waste of a computation. Let's say you go from the latent space to the pixel space, and you need to return to the latent space during the time of inference. So yeah, I think it's fair to say it's a waste of the computation power. So here are like several motivations to this talk, right? So here the solution is like we want to have some data-dependent approach. We don't want a generative model. We want something that is, let's say, non-parametric, because you need a lot of data to train the parametric model. So we just utilize the power of existing data in this scenario. So if we're doing this modeling, we want to reduce this gap between missing modalities and full modalities, because in the multimodal learning, if you have like two modalities, you have more features, then the model is going to perform quite well. But if this data point missed one modality, then it missed some features, then you're going to perform quite worse. Yeah, and finally we want a lightweight module. We don't want a super complex generator, right? Because that requires a lot of data, and that is super computationally expensive. Okay. Then the solution we have is the in-context learning. So the general idea is that we want to train a retriever first, and then use that retrieval model. We retrieve some data in your training set, right? And then using those retrieved samples, we do this in-context learning. And here we suppose these retrieved samples are full modality, so that you can remedy those missing modality data during the inference time. Okay. Then the benefit of this in-context learning is that we don't need to update any parameters during the inference time. Okay, here is an overview of our work. So we have a pre-trained multimodal transformer, and it's fixed throughout the training. Then in the middle figure, we want to retrieve out those similar samples during the inference time. And here as I mentioned, I only retrieve the full modality data. I don't retrieve the missing modality data, because here we want to help those samples with missing modalities. Okay. Then we have this in-context learning module. So this first sample is the test sample, and we have all of those context samples, and we use those samples to do this prediction, and it will output the Y. Okay, so there are several design choices in the in-context learning. Like, I think the most popular one is the so-called next token prediction. You just concatenate those samples, and you want the module to output the next tokens, from the first one to the final one. And the other one is not so fancy. It's the cost attention is just to refine the features based on those context samples, right? And we tried the two methods, and we also tried the mask modeling approach. Yeah, I will show the performance later. Okay, so we tried two data sets that are commonly used in medical domain. The Matthews data is from the MIMIC data set. And I think the first data set is to do the survival prediction. The second data set is to do the multi-level classification. Based on this data, we want to predict this phenotype category. And the final two data sets are kind of general. We have the language and also image as the input, right? And we have those mission states as shown here. So sometimes we only have maybe 20% of full modality data, and let's see how it performs. So here is the main result. So in this low data domain, and we consider this mission modalities, our method is in-context learning based on cross-tension is going to improve the baseline over all data sets. So the average improvement is about 6%. And we have all those figures about how this performance changes when you change the subsampling ratio. So from the left to right, you're going to have more and more data. So we consider in very extreme case that we only have 1% of the original training data. So in this case, this cross-tension based in-context learning is much better than one baseline last year. Yeah. And you may wonder, so you have a module during training, you're going to do the retrieval, right? So how is your model performing during the inference time? So we test this running time. It turns out, compared with this baseline, we kind of fine in terms of the inference time. But yeah, I think you can imagine that we took a lot of memory, I guess, because we have a model. And but yeah, I guess in terms of the inference time, is not so bad. And the takeaway is like, so we don't use those synthetic data. We just use this original training data that we collected, right? So I think it's fair to say in this case, it's better to use this original data, especially when you have very limited training data. The second takeaway is like, here we use the kind of non-parametric models. And it's better than parametric models. The last time when I presented this, I was caught by a statistician who is quite, who has strong opinion against this. But I mean, yeah, here I mean, in machine learning, I think this argument is held in this case. Yeah. And yeah, we want to do more applications using our method in the future, and also now. Yeah, and this work is done by a PhD student at UCL, and these are our collaborators. Yeah, and finally, I apologize to those who have listened to this talk once, or maybe twice. Yeah. But you are not alone, I think. I listened to Das talk twice. So, okay. So that's it. Thanks.
Do we have questions? Then let's, okay.
Hello. When you are talking about the real data is better than the generative data, so in what standard you are talking about that?
Standard is,
for example, a generative data probably is easier to get and to scale it up, and also it can provide more scalable or more diverse data.
Yeah, here we assume that in your application domain you don't have a lot of data, and it will be quite worse if you just use a general, generative models, and it will fail to generate those data in one specific domain. And if you want to fine-tune that generative model, you need a lot of data to fine-tune that. So that's why I think the region layer is better.
Let's thank you, Ziquan. And next presenter is Wu Yimeng from Camara University.